Is very warm good afternoon or good morning to one and all. I am Dr. Parameshwari. In this series, I'll give you detailed about the BIOMEMS subjects, concepts in small videos. So before that, in this video, we will see what is BIOMEMS. I'm going to give the introduction about the BIOMEMS. So what is mean by MEMS first? Before going into the BIOMEMS, we will see first what is MEMS. So MEMS, the abbreviation for the MEMS is Micro Electromechanical System. So that is a system which will combine mechanical and electrical functional which is fabricated in the micro level chip is called as MEMS devices. So that is a system which is based on the combination of mechanical and electro functionality, which size of the system is in the micro level. So that is less than the 1/10th of the human hair. So in order to fabricate this device, the main substrate, that is silicon, is used as a main substrate. So here we can see the size of the devices. So the size from 1 Armstrong to 100 nanometer is called as nanotechnology devices. If the size is between 100 nanometer to 1 millimeter, then the device is called as MEMS devices. Imagine the size, it is less than the red blood cell and less than the human hair. The above which, that is from 1 mm to 10 centimeter, the devices are called as mesoscale devices. Why this MEMS is advantageous? Since the customers today are demanding very smaller and lighter products, and also the small scale devices which act faster and have superior characteristics. Okay, and also it provides a precise and uniform quality when it is working, and it is a reliable component which consumes very less power when compared to the major devices, that is macro devices. So we can do batch fabrication. So with the batch fabrication, in a single batch we can manufacture many devices, similar like devices. Then the cost of the single device will become very less. Can you see the size of the devices, which is lesser than the coin? And so this device is called as seisonic microphone and micro thruster. Okay, this is called as micro thruster, and this is microphone, and this is micro thruster. So imagine the size of the devices. This much less size devices will occupy only very less space, less power, and the cost of the device is also very less. That is a very important. And how this MEMS has been arrived. What is the history of the MEMS? So the father of the MEMS is from the semiconductor devices. So 1939, the PN junction semiconductor is the first semiconductor device, and then in 1948 it converted as transistors, and then in 1954 the piezoresistive effect on semiconductor has been arrived, and in 1958 the first IC, that is integrated circuit, is identified by the J.S. Kilby. And in 1959 there is plenty of room at the bottom, and in 1962 the silicon integrated piezo actuators are developed, and in 1965 surface micro machine defect accelerometer, which is the first MEMS product. And then 1967 anisotropic deep silicon etching is the small scale device which is developed on the silicon. So this is how the MEMS has been arrived. And in 1977 the silicon electrostatic accelerometer. 79 it is like an integrated gas chromatograph, and then integrated pressure sensors, the Liga, batch fabricated pressure sensors like via vapor bonding, digital mirror display, commercial surface micromission, the accelerometers are developed in 1994, and 1999 optical network switch has been developed. So small by small development will lead to a miniaturized technology in 2020. So now in the recent, the available MEMS products are in various domains such as We can classify the MEMS in terms of two domain. One is sensor, micro sensor or micro actuators. So if you talk about the micro sensors, we have plenty of devices such as acoustic wave sensors, biomedical sensors, chemical sensors, inertia, optical pressure sensors, radiation sensors and thermal sensors. Likewise, we have plenty of micro sensors are available in the market. In the same way, if it is the actuator, then we have plenty of micro devices such as micro valves, micro pumps and microfluidic devices, electrical and optical relays and switches, grippers, tweezers and tongs in order to pick up the micro level devices. Linear and rotary motors. Likewise, we have plenty of micro actuator devices also available in the micro level in the market. Like, um, can anyone see the read-write heads in the computer storage system? Like a small head which will read the CD completely from start point to end point, which is the micro devices. And then the printer heads, inkjet printer head. So the size of the inkjet printer module is very less. For in order to print each character, the nozzle has to open, it has to fill up with the ink, then at the correct location at the correct time it has to eject the ink on the particular location. So this precise and micro level, imagine the precise and micro level actuation done on this inkjet printer heads. So we have micro devices components such as mini robots and toys also available nowadays. And in surgical, microsurgical and mobile telecom equipment are recently developed MEMS domain, which is very well developed now. And can you imagine the size of the, can you see this size of the MEMS product, which is very less than the pencil tip. So can you see this, which includes the inductor, cantilever, the piezoelectric sensor, CMOS circuits, capacitor, and everything is inbuilt within the single device. That is the advantages of this MEMS devices. As far as the BIOMEMS, in biomedical, we are using many sensors and actuators from the top of the body to the bottom of the body. So various cortical sensors are available in order to analyze the ICP, intracranial pressure, and cranial pressure sensor in order to sense the cranial pressure. We have visual prosthetic, auditory prosthetics, and we have cortical probes which is inserted into the cortical area in order to analyze the cortical sensors, and the pressure sensor, blood pressure sensors, pacemakers and joint ankle sensors, uh, and then bladder stimulator, smart musculoskeletal prosthetics. Like various sensors and actuators are developed for the biomems in order to have the diagnosis part as well as the therapeutic part. And why this miniaturization is required? How the miniaturization makes the engineering sense? What is that? Here, a small systems that is able to move or stop more quickly due to its low mechanical inertia. So it is thus ideal for precise movement and for rapid actuation. Wherever you want rapid actuation, then the size is very less, then it can able to do rapid actuation. And the miniaturized system which encounter less thermal distortion and less mechanical vibration because its mass is very less. And the miniaturized devices are particularly suitable for biomedical and aerospace applications because its size is very less and the weight is very less. So we can implant the devices inside the body. So the patient can carry the devices very easily without any interruption. And the small systems have higher dimensional stability at higher temperatures due to low thermal expansion. And the smaller size of these systems means less space requirements. And this allows the packaging of more functional components in a single devices. 3D devices can be manufactured within a single devices. And it requires only less material Because of the less material requirement, the cost of the production is very less and the transportation is easy. And we can do mass production and batches that minimizes the cost of the product. So these are all the major factor, that is miniaturization makes the sense. And what is there inside the MEMS? What are all the components of MEMS? I told you already, MEMS is categorized into two. That is, it is a sensor. It can be acted as a micro sensor, or it can be acted as a micro actuator. If the MEMS is acting as a micro sensor, then the block diagram will be look like this. That is, we have an input signal. That input signal will be sensed by the micro sensing element, and the sensed quantity will be transduced into the particular electrical event in order for the reading, and that is sent to the output signal. For example, like example is a pressure sensor. Take a pressure sensor as an example. For a pressure sensor, the input is a pressure. Pressure has to be sensed by the sensing element. So for sensing the pressure, here we are using a silicon diaphragm. So whenever if you are applying a pressure over a silicon diaphragm, the silicon diaphragm is able to bend. If there is a bending, then that bending has to be readed by or transduced by the electrical transducers. So here on the silicon diaphragm, we are using piezo resistors. So this piezo resistors will be act as a transduction unit that convert the amount of changes in the silicon diaphragm into the resistance changes. So this changes will be connected with the Wheatstone bridges. So we can, that is the corresponding pressure, the change in Wheatstone bridge will indicate the amount of pressure applied over here. Then the output signal here is read as a voltage changes from the transduction unit. So this is how the sensor is sensing, micro sensor is sensing. Like one more example, we have acoustic wave sensor. Here, acoustic wave sensor does not relate to the sensing of acoustic waves transmitted in solids or other media, as the name implies. So here the primary application of these sensor is to act like a band filters in mobile telephones and base stations. So it has some other applications also, such as sensing of torque and tire pressures, sensing biological and chemical substances, sensing wafers, humidity and temperature, monitor fluid flow in microfluidics. So for doing this, for this acoustic wave sensor, we have two sets of interdigital transducers. These are called as interdigital transducers, otherwise it is called as comb drive. Like a comb, we have comb, the device will be there, so that's why it's called as interdigital transducers, which are created by the piezoelectric layer attached to the tiny substrate. So when you energize by an AC source, the input IDT, that is input digital transducers, will be excited. So the finger electrodes in the IDT will get energized. So because of that, there is a movement of the comp electrode. Because of that movement, the surface deformation will be occurred in the tiny substrate. This surface deformation will create a stress over the output IDT. So that changes, any changes in the material property or geometry, because of that the torque will be generated. So the generated torque will be read out by the output signal. So here the acoustic, that is the sensing medium, will sense the information through acoustic manner. So that is why it's called as acoustic sensor. Now, how this MEMS is act as a micro actuator. In order for the actuation, the same like element, so here the same transduction element, we have a actuating element and the output action. So here we need to actuate some product with the help of the input signal. So for this, we have application called micro gripper. So which is the essential component in MEMS or micro level fabrications, because we couldn't take the micro level devices in the rough hand. So we need a gripper like devices in order to grip the smaller objects. So here for gripping the smaller objects, we have a device called micro grippers. For micro grippers, we have two sets of arrangements we have. One is vertical movement, the other one is a horizontal movement. These are all called fingers or arms of the micro grippers. So can you imagine this? This is the gripping arms. If you have an object in between this, that object has to be taken to one place to another place, then we need to grip the arms. So in order to grip the arms, we need to provide the voltage source here. When you apply a voltage here, then this electrodes will be energized. Then there will be EMF generation. That because of the EMF generation, this gripping arms will get energized. If it is energized, then these two will get closed. That is, the gap between the electrodes will get closed. Because of that, in between object will be gripped. When you release the voltage, then the gripping arm voltage will be released, then the object will be released. In the same way, here it is a vertical movement, here it is a horizontal movement. So this is called as COM drive actuators. So which is one type of actuation, that is we are going to do the function called gripping action. So we are going to actuate something with the help of the input. So that's how the micro level devices will be working based on the actuation. One more actuation using thermal forces. So here there will be a solid deform when they are subjected to a temperature change. Imagine we are having two sets of material. The material's thermal expansion coefficient is different. That is, alpha 1 is the one thermal expansion coefficient material, and the other material will have the thermal expansion coefficient of alpha 2. When the two sets of materials are sandwiched together, when it is subjected to the temperature medium, what will happen? This larger thermal expansion coefficient material will elongate more when compared to the smaller thermal expansion coefficient material. Then what will happen? When it is subjected to the same temperature, it will elongate more. When it is elongate more, it pulls the bottom layer down. So because of that, when the heat is applied, it elongate more. When it is elongate more, it pull down. So this can be used as a release. So when you apply the heat, it can bend down. It can act as a open. When you release the gate, once again it come back to original position. Then it is act as a off position. So we can do this as a micro switch or micro relays in MEMS products. So this is one type of actuations, micro actuations by using the thermal forces. So here the input is thermal forces. By using the thermal forces, we are doing activation like a switching action or relay action. This is how the actuation is done in micro actuators. Then what is microsystems? So we have a separate microsensor and a separate micro actuators. If you club together, that is, the microsystem is engineering that combines the MEMS component that are designed to perform a specific engineering function. That is, it will have sensor part, actuator part, signal transduction and conditioning part, and everything clubbed together. Then the system is called as microsystem. Okay, so this microsystem will work based on the closed loop feedback control system, and it have a sense, and the desired input will be sensed, and then transduction unit will convert the signal into the electrical format, and the signal conditioner will conditioning that, and the controller part will control, and everything will be stored in a device, and this input is used to actuate any particular element, and then the output will be taken in the form of action, that is actuation part. Then from there also, if there is any deviation, we can have a comparator that compare. If you want to do reverse action, then the controller will do reverse action. So we have a feedback system also. So this is how the intelligent microsystem is working. Then what are the MEMS and microsystem products? We have micro vias, micro mixers, and then various micro level products are available. Then what is the difference between microsystem and microelectronics? From the microelectronics only the microsystem has been developed. The microelectronic uses only single crystal silicon die, silicon compounds and plastic. But it is also uses the single crystal silicon die and few other materials such as gallium arsenide, quartz, polymers and metals. So it can transmit electricity for specific electrical functions. Microsystem performs a great variety of specific biological, chemical, electromechanical and optical functions. It is a stationary structures. In microsystem, we can have a 3D complex 3D structure, so it can move. It can have a moving components also. So it doesn't have moving structures. So the primarily it is a 2D structures. Complex patterns with high density over substrates. Here we can have a simple patterns over substrates. So here only fewer components in assembly. So here we have a 3D structure. So many components to be assembled. IC die is completely protected from contacting media. Here, sensor die is interfaced with the contacting media. Mature IC design methodology because it has a defined protocol to do the IC design. Here, lack of engineering design methodology and standards. Large number of electrical feed-throughs and leads. Fewer electrical feed-throughs and leads. Industrial standards available. Here, no industrial standards to follow. We can do mass production. Here we can do batch production or consumer based, customer based need productions. Fabrication techniques are proved and well documented. So here many microelectronic fabrication techniques can be used for the production. And manufacturing techniques are proved and well documented. So here distinct manufacturing techniques only used for the microsystem development. Packaging technology is also relatively well established. So here the packaging technology is at the infant stage. So these are all the differences between the microelectronics and microsystems. So hence the MEMS is a MEMS or BIOMEMS or multidisciplinary nature because we need to know natural science of the material in order to do the product. What are all the electrochemical process it undergo, we need to know. Then we need to know the electrical engineering in order to provide the power to the devices. We need to know the biology of the materials, molecular biology of the materials, plasma physics. We need to do the micro layer scaling devices. So we need to study about the scaling laws, quantum physics, molecular physics. We want to do mechanical, that is we want to do sensing and actuation part. So we need a mechanical engineering concepts knowledge, and we need to analyze the material engineering knowledge because we need to do materials for fabrication, materials for signal transduction, material for substrate, everything deals with the materials. And we do have the knowledge of industrial engineering also because we need to process the design, we need to do production control, we need to do micro assembly. And also for microfabrication, thin film technology, we need a chemical engineering also. So it combines the principal science and engineering disciplines involved in microsystem design and manufacture is wide variety. So it includes totally 7 natural sciences and 5 engineering areas such as electrochemistry, electrohydrodynamics, molecular biology, plasma physics, scaling laws, quantum physics, molecular physics, and in engineering it should contain mechanical, electrical, chemical, material and industrial engineering. Hence, the MEMS is called as interdisciplinary domain. So that's all about the introduction about the MEMS. Hope you understand what is MEMS. So in the next video, I'll tell you what are all the materials available for the MEMS. Thank you.